Hello and welcome to this breakout session on confidential computing with SUSE and IBM Z. My name's Adam Jollins and I work for IBM in the Z and Linux One team. And together with my colleague Mike Friesenegger from SUSE, we're excited to be here to talk to you about a major industry initiative called confidential computing and how SUSE and IBM Z can help you protect your data, your applications and your organisation. Security continues to be amongst the most important issues for CXOs. It became more challenging as computers moved out of the data centre and more challenging again with the emergence of the internet. And it's not just external threats. Internal threats through insiders stealing, deleting or changing data are as big or greater a threat and often harder to address because of the implied trust. Last year, IBM sponsored a study by the Ponemon Institute to look at the cost of insider threats. They interviewed over 900 IT and security practitioners at over 200 organisations, defining insider threats as a careless or negligent employee or contractor, or a criminal or malicious insider, or a credential thief. They found in the study that the average cost of an insider threat was $11.5 million, and that 60% of these organisations had experienced more than 20 incidents a year. This is scary stuff, especially if you consider that the insider threat has to succeed just once, but the security has to work every time. The principle of designing systems for zero trust is also becoming widely adopted. It's centred on the assumption that organisations should not automatically trust anyone or any other system, either inside or outside the organisation, but should instead continually verify. And that rather than relying on promises by system administrators or cloud service providers not to look at customers' data, it should be technically impossible for them to do so. To achieve this involves a combination of hardware, software and processes. There's also three areas of data security that need to be considered: data at rest, data in transit, and data in use. Data at rest is typically static data on a storage device. Protecting it involves encryption combined with access controls. Often only the most sensitive data has been encrypted, which opens up many vulnerabilities. But recent progress in on-chip hardware coprocessors has enabled the approach of pervasive encryption to become practical, encrypting all data by default. Data in transit is data that's being moved around, both across the internet and also within the data center. Again, encryption is key here, including using asymmetric cryptography and public-private key pairs. And finally, data in use, which is the data held in memory and being acted upon by the processor. Data is usually unencrypted for the time that it is being processed by the application, and so it's at its most vulnerable. So how does IBM Z support security today? Physically, the IBM Z as a centralized system is easier to protect because it has a smaller surface area vulnerable to attacks, combined with robust access control. Looking at the top of the picture, each IBM Z processor unit, or PU, then has an on-chip cryptographic coprocessor, or CPAC-F, which can provide hardware acceleration of symmetric cryptography, delivering much faster encryption and decryption of data at rest, and so enabling pervasive encryption to become practical. Moving down the diagram, the Crypto Express card performs two main functions. Firstly, hardware acceleration for both asymmetric and symmetric cryptography, including new algorithms. And secondly, secure storage of crypto keys in a tamper-respondent hardware security module, or HSM. And finally, Trusted key entry provides a secure way of loading cryptographic keys and offers a safer alternative to clear key entry. As you can see from this chart, the existing protections apply primarily today to data at rest and data in transit. Now let me hand over to my SUSE colleague Mike Friesenegger, who will describe in more detail how SUSE Linux Enterprise Server supports pervasive encryption on IBM Z. Mike, over to you.
Thank you, Adam. SUSE understands the importance of data security. Data is our customers' gold, which they use to drive their business. SUSE provides our customers the tools and technologies that can be used to protect our customers' gold. But SUSE does not do this alone. Rather, SUSE works closely with our partners like IBM Z to develop, test, and support these tools and technologies. SUSE Linux Enterprise Server has supported pervasive encryption for data in transit on IBM Z and Linux One for several years. The supported APIs include the library for IBM cryptographic architecture, better known as libica, which provides cryptographic functions for applications running on IBM Z and IBM Linux One, both with and without cryptographic hardware. The second API is called OpenCryptoKey for Linux on IBM Z or IBM Linux One. Applications that use this API can take advantage of the enterprise PKCS or EP11 coprocessor mode of the IBM cryptographic coprocessor. When working with IBM Z and Linux One, all data is stored on storage arrays that are attached to the system via storage connections. Protected volume encryption, which is another name, guarantees the data is secure while it is sitting on a disk in the storage array, as well as when it is transferred from the storage via the SAN. A secure key is stored in the tamper-proof hardware security module in the Crypto Express adapter and used to derive a protected key. The protected key is used by the CPAC-F on-chip hardware coprocessor to encrypt and decrypt the data at CPU speed. The latest versions of SUSE Linux Enterprise Server, including 12SP5 and 15SP2, have important components that enable pervasive encryption for data volumes. The kernel modules, pkey and PAES_S390X, interact with the Crypto Express to derive the protected key. The dmcrypt module is used by the kernel for device mapper storage, encryption, and decryption. Crypt Setup is part of LUX, also known as Linux Unified Key Setup, which is a Linux disk encryption specification. Protected volume encryption or pervasive encryption can use capabilities in LUX 2, the latest version of the LUX specification. Zkey and Zkey-Crypt Setup are tools from IBM. They work together to generate, validate, encipher secure AES keys in conjunction with the hardware security module and used on volumes encrypted with LUX 2. Pervasive encryption can be done using SUSE Linux Enterprise Server in an LPAR, a ZVM virtual guest, and a KVM virtual machine using GASD and fiber channel attached storage. SUSE extended the YAST partitioner to simplify the setup of pervasive encryption for data volumes. I'm using the text view of YAST in the next several slides, even though the GUI view will look very similar. This screenshot shows adding an LVM partition on DASDB. I have selected the encrypt device option, which is not a new option in YAST. What is new is the pervasive volume encryption option under Encryption Method. The encryption password is actually the LUX passphrase, which is used and required to access the LUX header on the encrypted partition. The passphrase does not play any part in the encryption, but is used to unlock the LUX header. The available APQNs represent the cards and domains in the hardware security module, which is part of the Crypto Express adapter. The secure key must be the same on the selected cards and domains. In this example, all of the domains 1, 4, and 5 are on card 1 and are assigned to this VM, but only domain 1 and 4 contain the same security key. If you want to see more, then I encourage you to watch the Technical Assurance for Confidential Computing using SLES on IBM Z and Linux 1 demo, where I go into more detail about setting up pervasive encryption for data volumes using YAST. After selecting Next on the second screenshot, we see YAST setting up protected volume encryption on several partitions, placing the encrypted partitions in a volume group and logical volume, and finally formatting and mounting the logical volume. YAST also sets up etc crypt tab so that the partitions are automatically mounted on reboot. YAST saves you time by not having to follow the very well-written IBM pervasive encryption documentation, as well as the additional steps needed to do LVM and disk formatting and mounting commands. So Adam, what's next?
So thanks very much, Mike. It's great to see how this works out in practice in terms of SUSE Linux Enterprise Server supporting pervasive encryption on IBM Z. So we've talked so far about data at rest and data in transit. The harder challenge, and the topic for the rest of this session, is protecting data in use. There's various possible ways of protecting data in use, but the leading one is based around data and applications being protected in an enclave by a combination of hardware and software, enabling the data to be held unencrypted in memory, which of course makes it much faster to process. And this is the topic area which the industry is calling confidential computing. It's probably helpful at this stage to just clarify the terms being used. Confidential computing is the term used for the industry initiative rather than for any specific technology or products. Trusted Execution Environment, or TEE, is the term used for technologies used to deliver confidential computing. An IBM Secure Execution for Linux is a trusted execution environment which IBM has developed for the IBM Z and Linux 1 enterprise servers, working in conjunction with our Linux partners such as SUSE. To support the industry evolution of confidential computing, a range of hardware, software and cloud vendors came together to form the Confidential Computing Consortium, which is a project and community hosted by the Linux Foundation with open governance and free participation. The scope of the Confidential Computing Forum is to promote the widespread use of hardware-based trusted execution environments. It was originally set up in October 2019, and since then the Confidential Computing Consortium has grown by 60% and above. The consortium has also written a number of white papers about confidential computing and is planning to host a developer summit later this year. Trusted execution environments have also started appearing on smartphones based on the ARM security extensions of TrustZone, and you may be already familiar with the idea in this context from your own use of smartphone apps. TEEs provide an isolated environment for applications to be securely processed without exposure to the rest of the system, for example, to hold critical financial data. So now we come to IBM Secure Execution for Linux, which provides a hardware-based trusted execution environment for IBM Z15 and Linux 1.3 systems, working in conjunction with the Linux distributions such as SUSE Linux Enterprise Server. Secure Execution provides a KVM-based virtual machine that is fully isolated and protected from the hypervisor, with encryption keys that only the IBM Z hardware and firmware have access to. It provides isolation between the KVM host and guests, helping protect against insider threats such as malicious administrators, whilst allowing honest administrators to manage and deploy workloads and go about their duties. You may remember the earlier IBM Secure Service Container technology, which provided a trusted execution environment at an LPAR level. LPARs provide a firmware-based virtualization of an IBM Z or Linux One, but only 85 LPARs are possible on a single system. IBM's Secure Execution for Linux builds on this and takes it to the next level, with isolation at scale, since KVM can then support hundreds or thousands of guest virtual machines. It can help protect and isolate workloads, both on-premises and in a hybrid cloud environment. So Secure Execution for Linux is designed to deliver secure multi-tenant hosting on a single system, as well as supporting regulatory compliance by being able to show the data is indeed isolated. Mike's now going to go into more detail about how SUSE Linux Enterprise Server supports secure execution and secure boot.
Although Secure Boot is not associated to secure execution, Secure Boot focuses on an aspect of confidential computing. With Secure Boot, an organization is assured that the Z and Linux One system and operating system kernel have not been tampered with, and the Linux kernel is coming from a trusted source. The trusted source for the SUSE Linux Enterprise Server kernel is SUSE. The firmware in the IBM Z15 and Linux 1.3 systems will check the kernel. If the kernel is not signed or cannot be verified, then the LPAR operating system load is canceled. The secure boot capability is new with IBM Z15 and Linux 1.3 systems. Currently, Secure Boot is supported for LPAR-based operating system loads using SCSI LUN where Linux is installed. The support for Secure Boot started with SLES 15 SP2 for IBM Z and Linux One. The link on this slide will take you to the IBM documentation to read more about Secure Boot. The first command in the screenshot shows that this is running on S390X architecture, which is an IBM Z or Linux One system. The second and third commands provide details about Secure Boot. We know that this is a Z15 or Linux 1.3 system when the has_secure option is enabled. The LPAR was booted securely because the second option, which is secure, is showing enabled. Searching the boot messages provided by dmessage also shows that this LPAR was booted securely and the Linux kernel boot signature was identified as SUSE Linux Enterprise. Now let's look at a screenshot of the HMC, or Hardware Management Console, and specifically the load screen for the LPAR called Zebra Echo 1 Charlie, or ZE1C. Notice the Enable Secure Boot for Linux checkbox is enabled. Also notice that the worldwide port name, also known as the WWN, and the logical unit number, or LUN, are being used. This confirms that this LPAR is using a SCSI LUN for the operating system load. What you do not see is that I disabled the Enable Secure Boot for Linux checkbox and clicked OK to continue the operating system load. In this final screenshot, you see that the secure option is disabled. The dmessage output also shows that the secure IPL is disabled. These two facts confirm that this LPAR did not secure boot this time when the operating system load was done. Now let's switch our focus to secure execution. The secure execution documentation focuses on the efforts of two personas. One persona is the cloud provider or system provider that manages the system where multi-tenant secure execution workloads will be run. The other persona is the workload owner who has a critical workload that needs to be run. Both personas are responsible for performing certain tasks in preparation for running a secure execution workload. The provider or system owner has the following responsibilities. 1, they have to manage one or more IBM Z15 or Linux 1.3 systems. 2, each system has a host key that has been built into the system during manufacturing. The provider must obtain and be ready to share with the workload owner the public key, which is part of the host key document. And thirdly, secure execution must be enabled via the HMC or hardware management console, or also via the service elements that are used to manage the Z and Linux One system. With secure execution enabled, the KVM LPAR must be started with the prot_vert kernel parameter. With this parameter enabled, a VM that is being started with the secure execution header will be managed by the ultravisor and run within the protected memory area that was created when the KVM host was started. Now, you may have said to yourself that I used a new term, ultravisor, which you're not familiar with. The ultravisor in the context of secure execution is comprised of trusted firmware that makes use of the memory protection hardware in the Z15 and Linux 1.3 systems that help enforce memory protection. This diagram from the IBM documentation about secure execution provides a great starting point to explain the responsibilities of the workload owner. Like I said on the previous slide, the workload owner is responsible for building the secure execution image. This slide helps dive a bit deeper into the tasks of a workload owner. The first step is to prepare the image, which contains the workload or application. This can be done using an image building tool like Kiwi or Manual or both. I prefer the approach of treating the image as code, so my recommendation is to build using Kiwi. I think an important thing to point out is to separate the application from the OS disk. Doing so should make OS and application executable upgrades much easier, or at least in theory. Because security of the workload and the workload data is paramount, encrypting the data and the OS are a must. The key used to encrypt the data disks can be securely included in the encrypted OS boot image. You may remember me talking about the host key document that the system provider has to share with the workload owner. The workload owner will verify the authenticity of the host key document. This proves to the workload owner that the chain of trust with the system provider and IBM is not broken, and the data within their workload will not be compromised. With the guaranteed chain of trust, the workload owner creates the secure execution header using gen port img and the keys included in the verified host key document. The boot image key is included in the secure execution header, which is used to unlock the OS disk and access the data key so the system can access the data. Finally, the secure execution image and data disks are sent to the system provider along with the XML definition for the KVM virtual machine. The system provider will define the VM and start the secure execution image with standard versh commands. I was hoping to demonstrate some of the tasks of the workload owner in the demo that I spoke about in this slide, but it wasn't possible at this time. I promise to work on using Kiwi to build a secure execution image and plan to publish a how-to guide before the end of 2021. So, in summary, there are 3 main areas of data security: data at rest, data in transit, and data in use. With confidential computing, that focus addressing on data in use. And with SUSE and IBM Z, you are well covered to address all 3 areas. Remember to check out the technical assurance for confidential computing using SLES on IBM Z and Linux One demo if you're interested in seeing a recorded version of the demos. From Adam Jollins and me, Mike Friesenegger, thank you for your time, and we look forward to continuing the discussion about confidential computing with you.